Hi, I'm Katie Miller, and today we are going to be talking about a problem where we have two spherical tanks. This one I'm going to call number 1, and this one is 2. And they are both open to the atmosphere. And the first one has a radius of 4 meters, and the second one has a radius of 2 meters. And so both of them have fluid in it. And the height of this fluid, the initial height, in tank 1 is 5 meters, and in tank 2 is 3 meters. And so both of these tanks have an inlet flow. This one we are going to call Q1 in, and this one we are also going to call Q2 in. And you'll notice that these both have pipes. There's one connecting 1 and 2, and there's one coming out of 2. And the area of these pipes are going to be the same, but we are going to call this one A12, and it is going to be 0.2 meters squared. And the second one we are going to call A2, and it's also 0.2 meters squared. And so what we want to do is we will set up Q1 in, the flow, let's go back. Not Q1 in, we already know that. Q12, so the flow between these two tanks. So Q12 we are going to set as A12, so the area of the pipe, times the velocity in between these two. And we are going to do the same and say Q2, so for this pipe, and we're going to do A2 times V2. And so what we want to find are these velocities. And so if we look at a problem that we have worked out before, sorry, that was a terrible drawing, close enough, where we had a tank with fluid in it, and we have this point 1 and this point 2, and there's a pipe coming out of it. We know that the pressure at 2 minus the pressure at 1 over the density plus the gravity times Z2 minus Z1, which is a distance, plus V2 squared minus V1 squared over 2 equals 0. And since these are at the same height, we can get rid of this, that's 0. And the velocity at 1 is going to also be 0. So we are left with 0 minus the pressure at 1, which is density times gravity times height over density, plus V2 squared over 2. This is going to equal 0. And so that gives us velocity equals 2gh, because these cancel out. So velocity equals square root of 2gh. And if we use that principle, then we can rewrite these equations. We can say that Q12 is equal to A12 times the square root of 2g, and the height here is going to be the absolute value of height 1 minus height 2. And we're doing the absolute value so that we don't end up with a negative sign under the radical. And for Q2, we are going to have A2 times square root of 2gh2. And so now that we have these, we are going to use mass balance equations to find the steady state equations that we will use in other videos to solve for the problem. So this is just setting it up. And so we'll start with dv1, so the velocity from 1 over dt this is going to be equal to Q1 in, so this flow in, minus Q12, which would be the flow coming out of tank 1. And so since we know that up here we wrote Q12 as that, we can rewrite this as Q1 in minus A12 times the square root of 2G absolute value H1 minus H2 absolute value. And so this is pretty good, but we need to compensate for sign change. So we are going to rewrite this as dV1 over dt equals Q1 in minus the sine of H1 minus H2, because we can't compensate for the sign under the radical, because if we get a negative under the radical, that just won't work out. So we have to compensate for it outside of the radical. So we add this sine of H1 minus H2, and we will multiply that by A12 times square root of 2G absolute value H1 minus H2. And so now that we have that, that will be our equation for V1. And so we're going to do another one, pretty much the same thing, for dV2 over dt. And so for this one, we are going to have Q2 in minus Q12, or I'm sorry, plus Q12, because Q12 is coming in and this is coming in, and then we are going to have minus Q2, because that is what is coming out of this tank. And so we can rewrite this with what we found above, so Q2 in plus A12 times 2G H1 minus H2 minus A2 square root of 2G H2. And again, it's the same thing. We have to incorporate the sign. So we are going to write it as dV2 over dt equals Q2 in plus the sine of H1 minus H2 times A12 times square root 2G absolute value H1 minus H2 minus A2 2G H2. And for this section, we don't have to compensate for the sign because we're not subtracting anything. H2 is going to be a positive value. And so to find the total velocity, dV over dt, we are going to have AC times dH over dt. And we want to find this dH over dt. And the AC is what we are going to have as our cross section. And so what we can do is write this as dH1 over dt equal to all of, dH1 over dt is going to be equal to dV1 over dt, all of that divided by the cross-sectional area of 1. And that will be the same for the second one. So we can put in, sorry, that was the wrong thing. We can put in the equation that we found for dV1 over dt. So this equation, can I copy this? I'm just gonna move it down here. Oh, where'd it go? Oh, it's down here. Sorry about that. So we're just gonna move it up. Oh, geez. Keeps doing that. Okay. There. Okay, here it is. We're good now. So now we have this, so we don't have to write it out again. So this is our equation for dv1 over dt, and we're going to have all of this divided by the cross-sectional area of 1. And we are going to do the same thing for height 2. We are going to have this equation. Let's see if I can do that better. Okay. This is not working. Oh, I think I got it that time. There we go. Okay, so we're going to have this equation come down here. And so this is going to equal this whole thing divided by the cross-sectional area of 2. And so these are the equations that we end up with for this part. And in the next video, we will be discussing the cross-sectional